Welcome back to the second part of sampling distribution. This video is for lesson 7.2, how sample means vary around the population mean. 7.1 is very similar to what we did in 7.1. In 7.1, we looked at how sample proportions vary around the population proportion. We're essentially doing the same thing, but we're going to have different formulas. Remember the two big things that we needed to find when we were doing this sampling distribution of sample proportion was the mean and the standard deviation. Let me try to find the formulas that we used for the proportions. Remember, the mean was the population proportion, P, and the standard deviation had that cool formula, square root of P times 1 minus P divided by N. So we used those two to calculate some probabilities. We looked at some additional examples, but what we are about to do in 7.2 is very similar. We're going to need to first talk about the mean and the standard deviation of sampling distribution of sample mean. So let's get there first. So let me close these 7.1 stuff. Now what I'm going over right now, I think my browser timed out. Let me go into Canvas and show you that the notes that goes with this is also posted on Canvas. My goal is to go over all the slides, the examples that I have here, and also I think it will be nice for us to go over some additional examples. So I posted those too. But this note, 7.2, is slightly longer than 7.1. Maybe because I just use bigger fonts, I'm not sure. But the blank notes is posted on Canvas for you. So let's go over this together, okay? Alrighty. So 7.1. I'm sorry, 7.2. I see somebody's in here. By the way, thank you so much, Brianna, for emailing me about this recording. I'm so glad you did. I was like, I forgot something, but I just couldn't remember. All right, so this is the second part of sampling distribution. You know what sampling distribution is. We talked about it in 7.1. What it is, well, you go out there and you ask, let's say, 30 people. Hey, what's your height? What is your height? You ask 30 people. You have a sample of size 30, right? And you record those 30 heights, and then you take the average of it. You take the mean of that sample. Well, that's called sample mean. You do that with another group of 30 people. Another group of 30 people, you keep on taking the same sample size of 30 somewhere else, just different samples. And if you record all those sample means and make a distribution of that, that's what we call sampling distribution of sample mean. So just like how we use the mean and standard deviation to solve some of these problems for sample proportion, let's talk about the two main results about the sampling distribution of the sample mean. First, the mean of the sample means, and look at the notation, I'll draw that Greek symbol mu with an X bar. Now this means the mean of the sample means. Now that sounds very confusing, but that's what I just kind of talked about. You go out and ask 30 people their weight, and you take the average of those 30 people. That's one sample mean. You go out there and grab another 30 people, and you find all their heights, and you calculate their sample mean. If you continue to do that, many times, you will get many number of sample of size 30. And what they are saying is, if you take the mean of those sample means, that's going to be equal to the population mean mu. So just like how the mean of the sample proportion was equal to the population proportion, the mean of the sample means is also equal to the population mean. Okay? So that's that. And don't worry, we'll look at all these applications, like examples, to actually use this, because I think in symbols it may look a little more confusing. All right, the second one, the standard deviation of sample mean, and look at the notation. We draw the little sigma for standard deviation, but do put the X bar next to it as a little subscript. That means the standard deviation of the sample mean. Because of course, those sample statistics will vary, right? Maybe one group may have a couple taller people and get a higher average height. and maybe the second 30 people that I interview was maybe a little bit shorter, so but they may have a slightly lower sample mean, but they're gonna vary, right? They're not all gonna come out to be the same. So we're gonna use the standard deviation to describe that variability. And here you go, here's a formula. The standard deviation of the sample mean is equal to the population standard deviation. You're going to divide that by square root of the sample size. Now, we'll talk about this later, but imagine as the sample size gets bigger, as the sample size n gets bigger, we'll be dividing by a bigger number, right? So what will happen to the standard deviation of the sample mean? We'll get there in a couple more slides later, okay? But now this guy is special. We have a name for this guy. Standard deviation of the sample means is also called standard error of the mean. So if you see that language, when you're doing the problem, they're just referring to the standard deviation of the sample mean. But now you know how to find two things: mean and the standard deviation of sample mean. We're gonna use them soon. All right. Say that the population that you're working with is normally distributed, and if you know that, well, it's very simple. If the population is normally distributed, then your sampling distribution is also going to be normally distributed. So for a random sample of size n from a normally distributed population having mean mu and standard deviation sigma, then regardless of the sample size, n can be small, n can be 4, 5, 6, or 10. What you know is that the sampling distribution of the sample mean is also going to be normally distributed with the same mean of that population mean at mu and the standard deviation, which we just call standard error of that formula. So in this slide, what you will need to know is that if they tell you that the population that the sample got sampled from is normally distributed, then the sampling distribution, regardless of the size of the sample, is also going to be normally distributed. Okay? So what if this little worrisome face, what if the population distribution is not bell-shaped or not normally distributed? Can we still use normal distribution to find all these probabilities in a sampling distribution of sample mean? And the answer is yes. Even when a population distribution is not bell-shaped, the sampling distribution of the sample mean can have a bell shape, and that depends on the sample size. Okay? So if you have a small sample size, then you have to make sure that you're getting the sample from normally distributed population. Otherwise, you can't assume normality. But, they never said anything about the distribution of the population, but you still want to know if the sampling distribution will be normally distributed. What you will need to use is something called the central limit theorem. And it's not that complicated at all. It says that if you got a sample size that is greater than or equal to 30, so 30 is going to be our number, are drawn from any population with mean of mu and standard deviation of sigma, then the sampling distribution of the sample mean approximates a normal distribution. Now, the key word that you need is this. That population can have any kind of distribution. It could be right skewed or left skewed. It doesn't have to be normally distributed at all. As long as your sample size is at least 30, then the distribution of that samples are going to be, sample statistics, is going to be normally distributed. So that's the second time. Now that's the second case. You either work with population that is normally distributed, but if you don't know anything about the distribution of population, then you must make sure that the sample size is at least 30 if you want to use normal distribution. So greater the sample size, the better the approximation will be, okay? All right. If the population itself is normally distributed, well, this is what we kind of talked about 2 slides ago, right? Then, without a doubt, the sampling distribution of the sample means is also normally distributed for any sample size n. So, if you got a sample size like 35, then we don't care about the population distribution. By central limit theorem, we know that sampling distribution will be normally distributed. But, it could still have a normally distributed sampling distribution if the population itself is normally distributed. Okay, so that's what these two things are talking about. All right, so this is a slide where we go over some examples. Now I got 1, 2, 3, 4, 5 different distributions up here, right? Take a look. The first one, it's a rectangular shaped distribution. This one is like a bimodal distribution. This one, would you call this right skewed or left skewed? This one will be like right skewed, right? Because the tail goes to the right side. And this one, I see 2 peak. I will still call this bimodal. But the very last one, all the way over, I don't know if you can see this. That's the only one that is normally distributed. Now say that these are the population distributions. No matter what the sample size is for the very last guy, the sampling distribution of this very last guy will always be normally distributed because the population itself is normally distributed. But take a look at these first 4. 1, 2, 3, 4. They are not bell-shaped, normally distributed population distributions. So if you take a small sample size, n equals 2, notice the sampling distribution for that one is actually a triangular. That's pretty fun. Sampling distribution doesn't look normally distributed at all when n is only 2. What about we increase that sample size? What if we increase that sample size to 5? Notice they turned a little more like a bell shape. This guy is still kind of skewed to the right, I would say. But what if you increase it a little more? Make the n to be 30. Now, n to be 30, the smallest sample size that you can have to assume normal distribution regardless of the population distribution. Look, all of them look pretty normal, right? All of them are now having that bell-shaped normally distributed sampling distribution. So that's what the central limit theorem was stating. Regardless of the shape of the population distribution, the sampling distribution becomes more bell-shaped as the random sample size n increases. Okay? All right. What else do we have? Another good picture of the same idea. Now, if you take a look at the population distribution, this guy is nowhere near bell-shaped or normally distributed, right? But if you take a sample size of n greater than or equal to 30 and make a distribution of those sample means, then what we know is that distribution will be normally distributed. But then the condition is what? N has to be greater than or equal to 30. But if you got a population that we know is just from normally distributed population, then doesn't matter what size n is, any n, the distribution of sample mean is always going to be normally distributed. I think we were talking about the same idea for the last however many minutes, but let's keep going. Mean of the sample mean. In either cases, either is from a crazy looking distributed population or normally distributed population, the sampling distribution of sample mean is always equal to the population mean. Okay? So there's that formula. They're just simply equal, just like the mean of sample proportion is equal to the population proportion. The mean is just going to be that. Now, variance, we really never use it, but the standard deviation is what we really want to use. So make sure you write down this formula down, that the standard deviation of sample mean, which is also called what? Standard error of the mean, is the population standard deviation divided by square root of n. So have this in your notes. We're going to be using these in our examples, okay? All right. Oh, it says increase the sample size. Let's read about this. For a random sample of size n from a population having mu and the standard deviation of sigma, then the sample size n increases. The sampling distribution of the sample mean x bar approaches an approximately normal distribution. By what theorem? By the central limit theorem. Okay, finally, let's look at an example. Average salary. Peter works numerous shifts as a seasonal waiter in a mountain ski resort. Experience from past seasons indicate that the salary for a shift follows a probability population distribution with a mean of 150 euro and a standard deviation of 6 euro. Now, write these two numbers down or highlight them. These are the population mean and the population standard deviation. We use them to find the mean and the standard deviation for sample mean. At the end of each winter, Peter randomly selects the pay stubs from 32 shifts. Well, look what we are just given. We got that n equals 32. He worked that season to check how much he earned on average per shift. He computes the mean salary per shift from the information on these pay stubs. So guess what? Guess how many sample mean he's going to have? He's going to have 32 different mean salary. Now we can make a distribution of that, and that's what we call sampling distribution of sample mean. All right, let's see what we're doing. Around which euro value would you expect his mean salary for shift to fluctuate? What are they asking here? What is the mean of the sampling distribution of his sample salary, right? Now remember, sample mean has the same mean as the population mean. So the mean salary per shift computed from the 32 pay stubs is a sample mean, a statistic from a sample of size n equals 30. So we would expect these sample means, one for each season, to fluctuate around the mean, a parameter of the assumed population distribution. And Peter already told us, based on his experience, that average is approximately 150 euro. So the mean of the sampling distribution or sample means is going to be the same as the population mean. So it's simply as that. It's just going to be 150. That one is not difficult because we don't really do any formula. We just have to remember that they are equal. But now, what if they ask you for the variability? For variability, you want to find the standard deviation. How much variability would you expect in the mean salaries from one season to the next? Find the standard deviation of the sampling distribution of the sample mean and let's interpret it, okay? Now, you got that formula down on your notes, right? So let's use it. Each standard deviation equals, remember to take the population standard deviation, which Peter gave us as what, 60 euro? Let me go back and double check. Was it really 60, Peter? Peter says, 6. It shouldn't, I got a typo somewhere. I don't know. Well, but I don't want to change the entire problem though. See, I thought I saw 6 euro, not 60 euro. But in my formula, I think I typed in 60. So that's a mistake that needs to be fixed. Let me fix that right now. How silly. But I'm so glad I just caught it. So it shouldn't be 60 divided by, or maybe, do me a favor, why don't you change that Peter problem? Why don't we change the, I know I'm not supposed to, but it's all right. Because I'm changing the original standard deviation to 60 euro because if I just change that number, then I don't have to change everything else in my slides. So if you can please change the standard deviation of the population to 60 euro for me, everything will be fine. So that's the population standard deviation. So in order for you to find the standard deviation for the sample mean, you use that formula. Divide that 60 by square root of the sample size. And remember, sample size was 32. If you do 60 divided by square root of 32, you will get 10.6 euro. Okay, 10.6. I shouldn't say euro, 10.6. So let's interpret this. From one season to the next, Peter's mean salary per shift would vary around the mean value of $150 with variability described by the standard deviation of 10.6. Now, here's my next question. Am I allowed to use the empirical rule in this case? Can I go ahead and say around 95% of this it's gonna be within two states? If we can assume normality, then we can make so many more statements about the probability. And the answer is, it looks like we're moving on to the next example. But then the answer is yes. Why? Well, not because they said this is from a normally distributed population, but because look at the sample size. The sample size was 32. It was greater than 30. So yes, we could have done more calculation from assuming that distribution, that the sampling distribution is also normally distributed. But then the first example, we were just talking about the mean and the standard error. All right, let's keep going. Okay, the next example, well, let's interpret the central limit theorem. Let me read this for you. A study analyzed the sleep habits of college students, because they can be pretty crazy. The study found that the mean sleep time is 6.8 hours. That's more than I expected, with a standard deviation of 1.4 hours. A random sample of 100 sleep times, and it's 100, guys. Guess what we can use then? Central limit theorem to assume normality of the sampling distribution of sample mean. But let's get there. Are drawn from this population, and the mean of each sample is determined. So how many means do they have? How many sample means do they have? Well, that I don't know. We just know each sample is of 100 different people. Find the mean and standard deviation of the sampling distribution of the sample means. Then they want you to sketch a graph of the sampling distribution. So look at this distribution for all sleep times. Would you say this is bell-shaped? It looks a little, this doesn't look bell-shaped to me. This is a little crazy looking distribution, but we know that the sampling distribution will be normally distributed. Why? Because that sample size is 100. Anything greater than or equal to 30, we know the sampling distribution will be normally distributed. I sometimes feel like statistics class is so wordy, don't you think? All these words that we use are just long and sound confusing, but if you know exactly what I mean by each term, they make sense. They will make sense. So hopefully you and I are on the same page. Hopefully. Okay. So what's the mean of the sampling distribution? You know that's always equal to the mean of the population, right? So the mu of x bar is 6.8. We know that because that's population mean was just given to us in the problem. But the standard deviation, remember you have to use the formula. They told us that the population standard deviation is 1.4. So remember the sample size of 100, we need to divide that by, we need to divide the population standard deviation by square root of 100. So if you do that on your calculator, you will get the standard error to be 0.14. So hopefully by now you are okay identifying the mean and the standard error of the means, okay? Since the sample size is much greater than 30, right? It was 100. The sampling distribution can be approximated by a normal distribution with the mean of 6.8 hours that we just found and the standard deviation of 0.14 hour, right? So we're gonna now do normal distribution. So if you graph it, it's going to be a bell shape. Remember that population distribution didn't look normally distributed or bell-shaped at all, right? But, well, the sampling distribution will be normally distributed because the sample size was much greater than 30. And that distribution will have a mean of 6.8 and the standard deviation of 0.14. Now you can see we're going to use these to find some probabilities later, right? But not just yet. We'll just keep on doing the same thing. Now this time, what's this? The training heart rates of all 20 years old athletes are normally distributed. Now look at this one. This is slightly different. Notice they already told us that this population is normally distributed. So do I care about sample size? Not really. Sample size could be smaller than 30, but our sampling distribution of sample mean will still be normally distributed because this is from a normally distributed population. And they are saying this population has a mean of 135 beats per minute and standard deviation of 18 beats per minute. We will use those to find the mean and the standard error of sample means. Random sample of size 4. Oh, notice how that sample is so small. It's 4. It's nowhere near 30. But we still know, because this population is normally distributed, we can still assume normal distribution for the sampling distribution. And the mean of each sample is determined. Find the mean and standard error of the mean of the sampling distribution, and they want you to sketch a graph of the sampling distribution of sample mean, which will be normally distributed, a bell-shaped curve, right? Now this is very nice because I was getting worried that sample size of 4 is so small, but we know the population is normally distributed. Well, regardless, we can still find the mean of the sample distribution. The mean is going to be equal to the population mean, which was just given to us as 135 BPM. The standard deviation, though, this guy, we have to use the formula, right? Divide the standard deviation by the square root of the sample size. So you do 18 divided by square root of 4. That gives you 9 BPM. Let's graph it. So you know that the mean of the sample mean is 135 with the standard error of 9. Sketch a curve. Put that 135 right in the middle. As you go 1, 2, 3 to the right, you will be adding what number? 9. And as you go to the left, 1, 2, 3 to the left, you will be subtracting 9. Okay? I bet you are now like almost pro at finding the mean and standard deviation now. Since the population is normally distributed, the sampling distribution of the sample mean is also normally distributed, even though the sample size was very small. Okay? All right. Why am I talking about this now? Because it's about time, guys, for us to find some probabilities. Let's do some calculation. So, you will need to find the z-score if you want to use the standard normal table. But we got this powerful tool called StatCrunch, so we really don't need this, but I still want to talk about it. So take a look at this. Remember, the z-score formula is simply value minus the mean, x minus x bar, and we divide that by the standard error, right? Now, or standard deviation. But we call it standard error if we're dealing with sampling distribution of sample mean. So this is going to be the z-score formula when we're working with sampling distribution of sample mean. You do x bar minus the population mean, and you divide it by the standard error. We'll practice this when we're going over probably the additional problems. We'll do these together later. All right. Example 1. Maybe we'll do it right here. The figure shows the mean distances traveled by drivers each day. You randomly select 50 drivers ages 16 to 19. 16 to 19, take a look. It's this one. 16 to 19 is the top car. Average miles driven each day. These, people in between 16 to 19 are driving about 20.7 miles each day. And they said information that we really don't need in here, right? 20 to 29, 30 to 49. But looks like we're only interested in drivers in between 16 and 19. So remember, their average is 20.7. What is the probability that the mean distance traveled each day is between 19.4 and 22.5 miles? Assume standard deviation is 6.5 miles. Notice they randomly selected 50 drivers, right? So we know N is 50. Let's put all these together and solve this. First, you're going to need to find the mean and the standard deviation, like how we did in the last 3 examples. So using the central limit theorem, the sample size is greater than 30, right? We selected what? 50 drivers. So we can use normal distribution. The sampling distribution of sample mean is approximately normal width. The mean is equal to the population distribution, which you read in the little chart, that pictogram, I think. 20.7 miles. So the mean is 20.7 miles, and the standard deviation, remember they gave us the population standard deviation was 6.5. Remember to divide that by square root of 50. If you do that, you will get 0.9 miles. You will always need to find these two values first. And we know this is normal. That means we can go on with it. So hopefully you're okay with finding the mean and the standard deviation. Number 2, let's find the z-score. So the z-score method, you need this if you're going to use the table or if you're going to use a table, you're going to need this. But I kind of want to just use the StatCrunch where we don't have to transform into z-scores. But I want to go over the traditional way, like, the regular way that you will need to do if you don't have the StatCrunch. So first find the z-scores for those two number of miles that they were giving us. So first 19.4 and 22.5. We need to find the z-score for both of them. Do 19.4 minus the mean of the population, which was 20.7, and divide that by the standard error that we found in the previous page. If you do that, the z-score for 19.4 comes out to be negative 1.41. Do the same thing for the 22.5 miles. You subtract 22.5 minus the population mean, which was 20.7, and if you divide that by the standard error, you will get 1.96. We need these two z-scores because we want to find the area in between these two scores under normal curve. So this is it. This is what they gave us, but what we just did using the z-score, we just kind of moved this to the standard normal distribution, the bell curve. But the area is gonna be exactly the same. We just transformed 19.4 into negative 1.41 z-score and the 22.1 into a z-score of 1.96. So what do we do now? Remember that table method that we used? We find the area to the left of 1.96. We find the area to the left of negative 1.41, and you simply subtract them. That's how you find the area under this curve, this blue area. So let's find the probability that the mean distance driven each day by the sample of 50 people is in between those 2 miles they gave us. Like we said, we can find that blue area that's stuck in the middle by subtracting how much is left of 1.96 minus how much is left of negative 1.41. And if you're wondering, where did they get these two numbers? Well, they got these numbers from just reading that table, remember? So let's maybe do that real quick. Let's see how much is to the left of 1.96. You guys have that bell curve or the standard table somewhere over here. Let me open it up. Remember the first number was 1.96, right? I open my bell curve. Let's find 1.96 z-score. Go to the positive side. 1.96, they said. 1.96. I'm looking at, okay. 1.96 is approximately 0.9750. 0.9750. 0.9750. That's what they did. They just read these numbers from that table. Now, I think at some point you stopped doing that because you figured out StatCrunch just does it for us. But that's how we would do it without those technology. You subtract those and we got that the sample mean, the chance that the sample mean comes out to be in between 19.4 and 22.5 is approximately 89.57%. So, of all samples of 50 drivers ages 16 to 19, see how they rounded up this number? 89 into a 90%. They said about 90% will drive a mean distance each day between 19.4 and 22.5 miles as shown in the graph. I don't think this is necessarily true nowadays because I don't know if you guys are driving at all, but I don't drive at all nowadays because we're all stuck at home. All right. This implies that assuming the value of mu equals if the population mean is really 20.7 miles, then about 10% of such sample will lie outside a given interval. So why is this helpful? I mean, think about it. Say that you go out there and you collect a sample of 50 drivers, and then you calculate their sample average of how many miles they drive. And say that you got something like, 24. There is only 10% chance such sample mean will be in that range. So you may be able to say, my sample mean just came out a little bit bigger. It really shouldn't be out here because, outside that region, there's only 10% chance that such values can happen. So why are we using sampling distribution? Just so that we want to be sure that the estimate that we're getting from our samples are going to be good estimate, a good measure to predict or the estimate the population parameter that we're really interested in. But it kind of feels backward, right? Because they gave us the population parameter already to find all these values. So, well, anyways, let's try another one. The mean room and board expense per year at four-year colleges, how much? $10,453. You randomly select 9 four-year colleges. Look at that tiny sample size of 9. So small, it's less than 30. What are we going to do? What is the probability that the mean room and board is less than $10,750? Now, it's only 9. Can we assume normal distribution? Look at the very last sentence. Assume that the room and board expenses are normally distributed with a standard deviation of 1650. Just because they added this piece right here, this problem is now doable. If we didn't know if this population was normally distributed, then we can't do any of this, right? But now we know it is normally distributed. We can use normal distribution to find this probability. All right, step 1. What do you need to do first? Well, we got to find the mean and the standard deviation, right? Mean of the sampling distribution is always equal to the population mean, which we were given as $10,453. But you got to find the standard deviation. And the rule is to divide the population standard deviation by square root of your sample size. The sample size was 9, so you're really dividing 1650 by 3. The standard deviation comes out to be $550. And we don't need that double equal sign there. Alrighty. So after that, let's try to get the z-scores to the left of $10,750. What is going to be the z-score of that? Now, in order for you to find the z-score, you need to use the mean and the standard deviation that we just found. So do 10,750 minus the mean, which is 10,453, and divide that by 550, that's standard error. If you do that, you get 0.54 to be the z-score. So this is nothing more than just z-score formula that you always use, but it looks a little different because we had to divide by the standard error, right? Now, what you need to do is go find the area to the left of 0.54 on that standard normal table. So let's find that. Where's my table? 0.54, right? Here is 0.5 and 0.54 is right here. So the area to the left of 0.54, it's 0.7054. So approximately 71%, right? Let's go back. So find the probability that the mean room and board expense is less than $10,750. And that came out to be, because we read it straight from that table, 0.7054. They didn't really write the interpretation, but that's what it is, right? What's the chance that the room and board expense is less than that amount? It's going to be about 70% chance. All right, I think we're looking at the very last example. All right, some college students use credit cards to pay for school-related expenses. For this population, the amount paid is normally distributed. Oh, yes! So we don't care about the sample size, guys. They're saying the population is normally distributed. So do not worry if they throw us the sample size of less than 30. With a mean of 1615 and a standard deviation of 550. So let's see what we do. Number one, what is the probability that a randomly selected college student, look, this is a randomly selected college student. This is not a sample of group of students. This is just a single student who uses a credit card to pay for school-related expenses pay less than $1,400. Now, this is not a sampling distribution, you see? This is just a single person. So do your normal distribution the regular way, the way that you know. In this case, you are asked to find the probability associated with a certain value of the random variable x. The z-score that corresponds to x equals 1400 is, let's find the z-score, x minus mean divided by standard deviation. 1400 minus the mean of 1650, and simply divide that by the 550, the population standard deviation. Because they're not asking you for the z-score for a group of sample, like we're not doing sampling distribution here. So z-score is just going to be the regular way that we're used to. So the z-score is negative 0.39. So if you find the area to the left of that z-score on the standard normal table, you will see that area is approximately 0.3483. And you do know how to read that on that table. So I'm just going to kind of go on. But I wanted to make sure that if they don't give you a sample size, they don't say, oh, we collected a random sample of 30 or 40 or 50 or 4, and then they just say, a randomly select a college student, you know, when you are asked to just find the probability associated with a certain value, then you don't really do that sampling distribution that we were doing today. So that's just going right back to the regular normal distribution that we talked about in chapter 6. Now, but number 2, take a look at this. You randomly select, 25 college students. This time, we are given the sample size of 25. So write down that n equals 25 this time. But we have to worry about this, right? Because 25 is not quite 30 yet. But can we still assume normal distribution for this sampling distribution? And the answer is yes, right? Because remember that little sentence, they told us that the population is also normally distributed. So n of 25, n equals 25, it's okay this time. Who used credit card to pay for school-related expenses? Is what is the probability that their mean amount paid is less than 1400? Now, it sounds about exactly the same, right, as the first one that we did. But in this case, your standard deviation or the standard error needs to be 550 divided by square root of 25. Because when they give you a sample size that they tell you that the sample size is 25, we're looking at a sampling distribution, not a certain value. So if you do that, the z-score came out, what was it, smaller? The z-score came out to be negative 1.95. Now notice they were very similar. They both had to do with less than 1400. But the first one was dealing with a certain value in a population, while this is talking about the sampling distribution. The probability this time is going to come out to be much, much smaller, 0.0256. Let's interpret this, okay? Why are they so different? Because they're talking about two different things. But let's compare the probabilities from part 1 and part 2. All right, so this is it. Although there is about 35% chance that a college student who uses a credit card to pay for school-related expenses will pay less than $1,400. Okay, there is a 35% chance, right? But there is only about 3% chance that the mean amount, a sample of 25 college students will pay less than 1,400. So what they are saying is, if you go out and do this sampling of 25 college students, there is about less than 3% chance that they will use less than 1,400, even though about 35% of them actually use less than 1,400. But if you take a sample of size 25, their mean is very less likely to be less than 1,400. So there's that slight difference between what the first probability and the second one is talking about. And well, they said one more thing, so let's read this one. Because there is only 3% chance that the mean amount a sample of 25 college students will pay is less than 1,400, this is an unusual event. Okay, so if you go out and you collect a sample from 25 college students and you find their average, there is a 3% chance that average is going to be less than 1,400, even though about 35% actually pay less than 1,400. That's the power of this sampling distribution of sample mean, right? Okay, I'll be back with additional examples because I think I did a lot of talking about what is what, a central limit theorem, but it will be very helpful to actually go over some of these problems together. So what I want to do is kind of go over about 4 problems that will help you on homework number 15 through 28, and that one I'll do that on my iPad, so I'll be back with that video very shortly. Okay, see you later.